Hello everyone, this is Ziyu from LAMP at the University of Pittsburgh. Today I'm going to introduce my research on fully embedded silver microgrid as flexible, high-performance, transparent conductor. Before that, I would like to thank my advisor Paul Liu and collaborator Melps. Also, thanks to DOE for financial support. So, what is transparent conductor? It is an essential component to many applications, such as OLEDs, smart window, display, solar cells, sensor, and e-paper. Two unique properties are transparent and conductive. For transparency, materials need to have a wide band gap to be optically transparent. At the same time, electrically conductive is very important to make less energy loss. However, take thin film as an example. The thinner the film is, the higher transparency, but less conductive. As a result, the key to reach a high-performance transparent conductor is to balance the resistance and transparency trade-off. Currently widely used materials, including doped oxide, metal nanowires, carbon-based nanomaterials, and metal meshes are well investigated, but there are still some challenges. For example, the brittleness and high cost for ITO, low surface quality of silver nanowires because of junction-to-junction contacts, overall high resistance for carbon nanotubes, and some oxidation issues while heating for copper. Then, what are other possible solutions? Yes, microgrid. Think about our mentioned key, transparency and resistance trade-off. The transparency can be easily manipulated via varying pitch in line with, as shown in the left figure. Furthermore, by increasing the thickness of microgrid can effectively lower resistance without sacrificing transparency. Some other works utilize graphene as a protective layer to enhance the adhesion to the substrate. This step can be simplified by introducing another structure called embedded microgrid. Here is the process flow of fabrication. First, for the lithography process, a nice pattern is formed by spin coating a layer of photoresist, a special polymer which is sensitive to visible light. Then develop an exposure. Reactive etching procedure was done to expose part of substrate. A particle-free silver ink was spin-coated onto the samples. This ink can achieve conductivities up to 90% of bulk silver with low annealing temperatures, which is a direct replacement for nanoparticle inks and metal paste. After curing and photoresist lift-off, we can get the fully embedded microgrid within the substrate. On the right figure, we can see the photo and SEM images showing the nice and uniform grids all over the substrate, including rigid glass and flexible PET. A superior performance was demonstrated. A high transmission and simultaneous low shear resistance. Haze is resulted from wide-angle scattering. Our low haze value also indicates a good clarity. To test the sample durability or reliability, bending, peeling, and folding tests are performed. As we can see, compared to ITO, embedded microgrid show a significant increase of durability. In conclusion, applying the embedded silver microgrid is an effective and competitive alternative to replace the current ITO technology. This method is also compatible with multiple substrates, both flexible and rigid situation. The microgrid samples has a high transparency over 90%, a low haze value with low shear resistance as well. Some other future work are also presented here. This method can integrate the silver microgrid into optoelectronic devices, which can boost the performance. High throughput fabrication process is preferred in the future. Some other broader applications, including electromagnetic interference shielding, so-called EMI shielding, and biomedical sensors, will be very important in the near future. Thanks for your attention.